Okay, so I want to continue talking a bit about Dynkin diagrams. I've been threatening to talk about E8, which is a specific example of the theory that I happen to love. It's like the biggest, most complicated, elaborate, strange Dynkin diagram. But I keep putting it off, and I'm going to put it off yet again because I realize that it's probably more important to cover the general theory before I dive into these slightly exotic examples. So I've showed you how Coxeter diagrams are used to classify finite reflection groups. So those are finite groups of linear transformations of Rn that are generated by reflections along various vectors. And then we took the next step and saw that Dynkin diagrams, which are Coxeter diagrams with some extra structure, are used to classify, well, basically finite reflection groups with some extra structure. They're called root lattices. So a root lattice is a lattice of points in Rn. So a finitely generated abelian group of maximum rank that you can fit in Rn that have a finite reflection group acting as symmetries of them, but they're even more tightly connected than that because the finite reflection group is generated by reflections along some of the elements of the lattice, some of the generators of the lattice, which are called roots. So all of that's very nice, but when you actually normally encounter the theory of Dynkin diagrams in most contexts, you will hear that they're used to classify something else, which is what I want to talk about today, and that's semisimple Lie groups or semisimple Lie algebras. So that's what I want to talk about now. So if you're a category theorist, you can just say a Lie group is a group in the category of manifolds. And then if you know what manifolds are, you're done. If you're a normal person, I will still assume you still know what a manifold is. I guess I'm not a truly normal person, but you could say the same thing more slowly like this. So a Lie group is a group P that's a smooth manifold. I'm not interested in any other kind of manifolds. So a manifold is a space that locally looks like Rn, such that the multiplication map, for starters, is smooth. So we have this map M from G times G to G, and we want that to be smooth, but also just be careful. We should maybe say the inverse map, setting any group element to its inverse, are smooth. So smooth maps, in infinitely differentiable maps, are the nice kind of maps between smooth manifolds, and that's basically what you mean when you say a Lie group is a group in the category of smooth manifolds. We're just sort of taking the concept of group and sticking smoothness in everywhere in the definition. And so then you also worked for the maps between those. So a Lie group homomorphism say like F from G to H is a homomorphism between Lie groups that's smooth. So, for example, Rn with its usual addition is a Lie group, but a more interesting example would be the group of all rotations in three-dimensional space is a Lie group, and there are lots of others, lots of examples that we'll be seeing. So when people decided to try to understand these, they realized that part of what's so nice about them is that you can reduce a lot of problems about Lie groups to problems in linear algebra, because you can associate a vector space to any Lie group. So any Lie group G has, for starters, a vector space, which I'll call Lie of G. And what it is it's the tangent space to the Lie group at the identity. So any manifold, by which I mean smooth manifold, has at any point in it a vector space called its tangent space. And you should just imagine a manifold as like a sphere-like thing in some higher dimensions, and the tangent space is just being like a tangent plane to that thing. So this is basically what a sophisticated differential topologist is secretly thinking when they say these fancy words. But this, because G is a group, it gets to have more structure than just a vector space. It becomes what's called a Lie algebra. Yeah.
Sorry, just going back a bit. Would that be naturally the same as a smooth manifold in the category of groups?
That's harder to define because you can't usually define smooth manifold in any old category. And so I wouldn't, so, I mean, if you can figure out how to make sense of it, then the answer will definitely be yes. But algebraic structures like groups, rings, and so on, they're very easy to put inside any category because you just take the equations, write them as commutative diagrams, and stick them in whatever category you want, as long as the category has enough good stuff, like your products. But sticking topological concepts into other categories is sort of harder, or differential concepts. So that's what. But there is a principle called commutativity of internalization that says that when both of those kind of things make sense, they're usually the same. So there's a map, and now I mean a smooth map. There's a map called the exponential from the Lie, from this vector space, Lie of G, to G. So very often the way it works is that G is some group of matrices. Lie of G will be some vector space of matrices, and this exponential map will be defined in the usual way, namely by formal power series, or not so formal power series, actually convergent power series. So this is what it would be if G is a group of matrices, say real matrices. But so that's all I want to say about it. And then what it lets you do is it lets you define a bracket operation, a binary operation called bracket on the Lie algebra. So this vector space gets a kind of multiplication-like thing called the bracket. And the way it works is this. So if I have two elements, X and Y, in the Lie algebra, I define in the Lie algebra, vector space, tangent space of the identity. What I can do is I can exponentiate one of them times a real number, exponentiate the other times some other real number, and then do kind of a commutator trick. So exponentiate minus the first one, exponentiate minus the second one. And then I can differentiate this stuff with respect to the two real parameters S and T, and then set S and T equal to 0. So you see this quantity here, I mean, it may not be obvious that this actually makes sense as an element of the Lie algebra, but it's true. You can check that this is actually well defined as an element of the Lie algebra. And one thing you can more easily check than that actually is that if these exponentials all commute with each other, then this thing here is just the identity, and so you're going to get 0. So if you have an abelian Lie group, then this Lie algebra bracket here is going to be 0, and you call that an abelian Lie algebra. But you can think of the bracket in general as telling you how much the Lie group fails to be commutative. And the amazing thing is that a whole lot of information about the Lie group is just captured by this Lie algebra. For starters, I'm not going to use these axioms at all, but this obeys some axioms, making Lie of G into a gadget called a Lie algebra. And at first, I was going to not even write down the axioms, but that seems sort of tantalizingly close to explaining them without actually getting there. So, I mean, I'm not really going to explain them, I guess, but I'm just going to say what they are. So the Lie bracket is linear in each variable. So here I'm just writing linearity in the second variable. So here X, Y, and Z are guys in the Lie algebra, and A and B are real numbers with the real vector space. Instead of writing linearity in the first slot, I'll just subsume that by this fact that the Lie bracket is anti-commutative, anti-symmetric. So that implies that it's linear in the first slot as well. And then the really exciting one is that the Lie bracket is a derivation of itself. So it obeys a product rule for itself. So if you think of X as differentiating the bracket XY, you might hope for some kind of product rule where you first differentiate Y, and then multiply by Z, and then and then differentiate Z. So this is formally product rule, but it's amazing, right? Because the differentiation operation is this bracket, which is the thing that it's a derivation of. So it's very self-referential product rule called the Jacobi identity. And you can prove all these things starting from this formula and doing some calculations. So that's the definition of a Lie algebra. And I'm merely presenting it to let you know that I can talk about a Lie algebra that's not one that comes from a Lie group. It's just a vector space with a bracket that has that stuff being true. Now, the cool part is that we can almost, I guess you could argue about how almost this is, but we can almost recover a Lie group from its Lie algebra. So here I mean the Lie algebra with this bracket operation. And this is why Lie algebras are so popular, so useful and important, because they capture the information of the Lie group to a large extent, just in some linear algebra stuff that's much easier to work with. Now, this isn't, you can't really recover a Lie group from its Lie algebra for two main reasons. So first of all, the Lie algebra only knows what's going on near the, well, they're both due to the fact that the Lie algebra only knows what's going on right near the identity of the group. So if your group had several connected components, for example, if your manifold G had several connected components, the Lie algebra couldn't possibly know what's going on in those other connected components. So that's one problem. So G will have the same Lie algebra as the connected component of the identity. So I'll just call the identity component. So that's one thing you just have to accept. Indeed, any finite group, for example, is a Lie group, but it's a zero-dimensional Lie group. It's just a discrete set of points. In that case, the Lie algebra is zero-dimensional and it doesn't know anything about what the group is doing. So what we do typically is focus most of our energy on Lie groups that are connected so that we can use the algebras to greater power. And then also, G will have the same Lie algebra as any covering space of G. If G is connected, actually any covering space of G gets to be a group as well. But maybe, so you can talk about a covering space, that's a Lie group. Where the map is a homomorphism of Lie groups. So again, if you have a covering space of a manifold, it's again a manifold, but if you can't tell whether you're on the original manifold or the covering space unless you walk around for quite a while on your manifold. So for example, the circle is a manifold and indeed a Lie group, and it has a covering space, which is the real line, which I'm drawing as a kind of spiral staircase here, so that the covering map is just vertical projection downwards. And if you're a little guy walking around on the circle and you don't take a grand trip around the circle, you won't really know that you're on the circle rather than on the line. And in particular, anything you do about the Lie algebra will be just the same. So that there's no way you can tell. Yep.
A question about what you just erased. The question is whether the definition of the Lie bracket automatically confers that the Jacobi identity is satisfied.
Yes, it does. Yeah. So usually if you take the case of a matrix Lie group where they're matrices and you write down that definition of the bracket and write the exponentials down as the way it did as a power series, you can just calculate away, and by the end of this talk, you'll have proved the Jacobi identity. It's just a calculation of sorts. Yep.
When you're thinking about Lie groups in particular, thinking about Lie groups acting on manifolds, you often come to a point that you sort of realize that you would have preferred to have defined the Lie brackets with a minus sign, in the sense that if you define it in the standard way and you have an action of a group on a manifold, you get not
you know too much, but yeah. So
so I was wondering, do you have any reason to choose this convention rather than minus?
No. One great thing about a Lie algebra is if you switch the bracket to minus itself, it's again a Lie algebra, very much unlike a ring or something like that. So go ahead, switch it. I won't notice. Yeah. So yeah, that's yeah. So okay. So in particular, any Lie group G has the same Lie algebra as the universal cover of its identity component. So that's a covering space that covers all covering spaces, all connected covering spaces. So this guy here is going to be both connected and simply connected. So that just sort of shows some of the limitations of my original claim that you can almost get the Lie group from the Lie algebra. But it turns out that this is sort of the only kind of stuff that goes wrong. So there's a theorem which I'll just phrase in the language of category theory, just because it's so fast that way, that the category of Lie algebras, and I mean finite dimensional ones. Remember, all my vector spaces in this course are finite dimensional. So the category of Lie algebras is equivalent to the category of connected and simply connected Lie groups. So we have this category of Lie groups and smooth homomorphisms between them. But if we look at the subcategory where you just restrict to the objects that are nice like this, connected and simply connected, then that's equivalent to Lie algebra. So the idea is that from such a Lie group, you can get a Lie algebra, but also from such a Lie algebra, or from any Lie algebra, you can get a connected and simply connected Lie group, and those processes are inverses of each other up to natural isomorphism. So classifying connected and simply connected Lie groups is just the same job as classifying Lie algebras. And that's great because it reduces the problem down to what's essentially a linear algebra problem. Unfortunately, it's an incredibly hard linear algebra problem still. So Lie tried to classify Lie algebras, and he classified the one-dimensional ones, then he classified the two-dimensional ones, and then he classified the three-dimensional ones, and maybe even got to the four-dimensional ones, and it got harder and harder each time. And by now it's known that that's sort of a hopeless business, sort of like trying to classify finite groups, all finite groups or something like that. So we have to simplify things further if we're gonna get anywhere. Yep.
Do you mean compact Lie groups? SL2R and spin 3 have the same Lie algebras?
No, they don't. They don't. Sorry, that's the most honest answer to the question. But I'm about to mention compact Lie groups. If I want to be more diplomatic, I'd say I was just about to talk about compact Lie groups. But I'm very undiplomatic. See, so what we do to try to get something that we can classify is that we look at compact Lie groups. Then we can classify them, and I'll define a compact Lie group. That's a weird, compact Lie algebra. That's a funny word because it's a vector space, so it's basically almost never going to be compact. But what I mean by that is the Lie algebra of a compact Lie group. Isomorphic to the Lie algebra of a compact Lie group. And it turns out that these we can manage to classify. So the first big theorem is that every compact Lie algebra is a direct sum of two different kinds. So you can take direct sums of Lie algebras and get new Lie algebras. And you can always write it as direct sum of an abelian Lie algebra. So abelian Lie algebras are the easiest ones. These are ones where the bracket of any two elements is just 0. And then, more interestingly, a so-called semi-simple Lie algebra, really a compact semi-simple, but I'm just going to define semi-simple Lie algebra. And those are sort of the furthest away from being abelian. There are lots of ways to define them, but the fastest way is to say that if you give me any elements, you can write it as the bracket of two other elements. So everything is a bracket of something, as opposed to only 0 being a bracket of something. If you know other definitions of semi-simple Lie algebra, then you can think about why this is equivalent to those, but this is just faster to say, and it sort of illustrates the radical opposition between the two kinds. So now abelian Lie algebras are incredibly easy to classify, so it's just the semi-simple ones to focus on. So there's one of isomorphism, there's just one abelian Lie algebra of each dimension. Namely this, Rn with the bracket just being 0. And this is the Lie algebra of a compact Lie group. This is the Lie algebra of the torus. The torus Tn is the product of n copies of the circle. And that's an abelian Lie group, so it's got an abelian Lie algebra. So that's sort of simple to study. But these semi-simple ones here, despite their name, are not so easy to understand. But the good news is that they can be understood. So it turns out that they're classified by Dynkin diagrams. So there's a one-to-one correspondence between isomorphism classes of compact semi-simple. Sorry. I want to introduce a word. So, yeah, no, I don't need to introduce that word yet. So when I say a compact semi-simple Lie algebra, I just mean a compact Lie algebra that's also semi-simple. So I guess I started to find that already. So there's a one-to-one correspondence between those things in Dynkin diagrams. More precisely, there's a one-to-one correspondence between isomorphism classes. You always classify things up to isomorphism of compact semi-simple Lie algebras and Dynkin diagrams. Now, I said that you could get these Dynkin diagrams that have several pieces, the non-connected ones. And then we focused on listing the connected ones. But here I want to allow the not necessarily connected ones that are built out of those connected pieces. So this is great. And I took a course when I was in grad school where the main point of the course was to prove this and to classify all those Dynkin diagrams. And I hated it. I hated it because I didn't understand what was going on and why all the definitions were being made. And it took me much longer to get to the point of being able to appreciate these things. So I'm hoping that by leaving out all the hard stuff, it will be a little easier to appreciate it at a very rapid pace, but I also know that maybe it won't work. Yeah.
It's not going to be so rapid, so I'm going to ask you questions from Zoom.
Okay.
So can the theorem in some way be made categorical? In other words, can you define a notion of morphism between Dynkin diagrams such that this becomes an equivalence?
Not in any good way. I mean, you'd want to make it so that it would match the concept of morphism between Lie algebras. And the only way I know to do that is basically to tell you how to get a Lie algebra from a Dynkin diagram, which is sort of the hard part that I'm not going to talk about, which is the reverse. I'm going to tell you how you get from one of these Lie algebras to a Dynkin diagram. But basically, no, I don't think there's a good way to do that I know of anyway. I really don't think there's a good way. It's a good question, but I don't think there's a good way. So, okay, so how do we do this thing? So G is going to be a compact semi-simple Lie group here. We're going to process it until we get a Dynkin diagram. So it's Lie algebra is going to be one of these compact semi-simple Lie algebras. But the more interesting first step is that G always has a bunch of subgroups that are tori. And it always has a maximal subgroup that's a torus, the biggest possible subgroup that's a torus. Now it actually has lots, but they're all sort of the same. all such things are conjugate to each other within G. So if you've got a maximal torus P prime, and I've got a maximal torus T, I can find some group element to conjugate all the elements of my maximal torus to get yours. So that's why people often talk about the maximal torus, even though it's sort of misleading in some ways. So we'll pick one, and then we'll do some stuff with it. So the Lie algebra, Lie of T, it turns out that this thing gets an inner product. It has a God-given inner product on it. The vector space, but it gets a God-given inner product on it, which I will not write down the formula for. So that means Lie of T is isomorphic to Rn as an inner product space, as a vector space with an inner product. Now you'll notice when I was talking about finite reflection groups, I was talking about them as transformations of Rn. But if I'd been more smart or something, I would have said there are subgroups of transformations of some inner product space. So anyway, we're Lie of T, we'll just think of it as being Rn. Then we'll start bringing in reflection groups, finite reflection groups and such. Now we have this exponential map, as I mentioned, from any Lie algebra to its corresponding Lie group. So we can do that for this torus. But because T is abelian, it turns out that this exponential map is really nice. It's actually a group homomorphism, a Lie group homomorphism. Notice that a vector space is a Lie group. So Lie of T, you can think of it as a Lie group, even though it's a Lie algebra. So it makes sense to say that this is a Lie group homomorphism. And the picture should be something, well, I'll bring in the picture in just a second to help you out. So you can talk about its kernel. Let me call that L. So that's some subgroup of Lie of T. And it turns out that that's a lattice. A lattice in this vector space, Lie of T. So the picture should be something like this. T is a torus. One way to think of a torus is that you can get it by taking a vector space and modding out by a lattice, in fact. So if I have a lattice in a vector space, I can take any one of these sort of fundamental cells here and curl it up, identify opposite edges, and I get a torus. So here I have this lattice sitting inside the vector space Lie of T. And then if I curl it up, that is, I identify 2 points in this vector space. If they differ by a point in the lattice, I curl it up, then I get this torus. The process of modding out by the lattice. And I'm claiming that is just the torus. And that this map, this modding out map, it is just the exponential map. So the kernel of the exponential map is this torus. So starting from this torus, we get a vector space with a lattice in it. So we're getting within shooting distance of Dynkin diagrams. But the good news is it really, really works. This L is actually a root lattice. It's a very symmetrical lattice, indeed a root lattice. Root lattices, remember, are these things that we saw were classified by Dynkin diagrams.
John,
Yes.
this is, I mean, the usual definition of root lattice I've seen involves looking at the action of Lie of T on Lie of G, and then you get the roots that way. And I cannot, I mean, can you explain why?
So I explained why it's, explained why it's a lattice. Okay,
Why is it the root lattice?
okay, well, what I'll do, yeah, well, I don't know. Yeah, so what I'll do is I will show you that there is a finite reflection group, or I'll show you that there's a group that I claim is a finite reflection group that's acting on L. I'm leaving out all the stuff that may be a quarter-long course, right? So I'm afraid it's gonna be incomplete in various ways, but so the point is, there's a group called the Weyl group of G, which is the collection of all group elements that when you conjugate your torus by them, you get back that same torus. It really depends on both G and on our choice of torus. But as I said, all tori are conjugate to each other, so you get an isomorphic Weyl group if you pick another torus. So you're talking about the Weyl group. So this acts on T by conjugation, by this action. And so therefore it acts on everything that we've associated to T. It acts on Lie of T as linear transformations, and it acts on this to preserve this lattice, which is the kernel of this map here. So I'm not proving to you that this is a finite reflection group. I just don't have time, but it is. And I'm not proving that these reflections that generate it are actually reflections along certain vectors in the lattice L. These vectors I call roots, but it's true. So sorry, it's very sketchy, but the real big news is that moreover, we can, this is like the least believable claim, that we can reconstruct the Lie algebra, the bracket, from the lattice and this group acting on it. So from the root lattice. This takes real work. So basically, the action of the Weyl group on the lattice contains enough information about commutatory type stuff to let you actually be able to figure out the bracket in the Lie algebra. Yep.
See, what you're trying in that second line there is not the Weyl group, it's the normalizer of the torus. For example, it contains.
It's the normalizer.
Absolutely not a finite group.
Okay. Yeah. Good. Yes. So modulo the centralizer of the torus, modulo the things that act trivially. Thanks. Yeah. GTG equal to T. Yeah, so this is too big. It includes the torus, for example. So if you mod out by that centralizer, this is like the normalizer mod the centralizer, then you get the mod. Thanks. Yes.
Excuse me, you had some information on the previous board and that I forgot the details of.
That's probably good, right?
Is there any condition on the group other than that it's Lie algebra is a Lie algebra that you want? Because in the conventional sense, you have the adjoint form.
I started out with a compact semi-simple Lie group, which I had defined to be one that was compact and whose Lie algebra was semi-simple. So that's where we are. That's what you.
Because in sort of the conventional approach to the story, I know the root lattice is the lattice in this sense that you obtain if the group is the adjoint form. and then you get
Oh,
finer lattices. But
Yeah,
here the statement is that even these finer lattices are all root lattices in the way that you define it. So,
to get, you're right. To get the traditional. Yeah, you're right. To get the standard notion of root lattice, we need to take. G to be so there, G could have various covers that have the same Lie algebra. And at the top, there'd be like the universal cover, which is simply connected, and at the bottom is the one that's sort of the least simply connected, and that's this adjoint form. And that's the one you want to get the traditional root lattice. Yep, so I may have needed to insert that condition in here too. Yep. Yes, thanks for all these corrections. So in the end, what we get is a correspondence between three things. I don't think I'll say this because I basically said most of it. So there's a correspondence between Dynkin diagrams, compact semi-simple Lie algebras, and then connected and simply connected compact semi-simple Lie groups. Those are three equivalent things. So what I would think I want to spend my remaining time on is, instead of like writing that theorem sort of over again, is to do an example. That's more useful, I think. So let's do SUN. So that's like the n by n complex unitary matrices with determinant 1. But for concreteness, I'll think about SU3, so I can draw some things, but everything I say should work for other n. So if you take SU3, what's a maximal torus? Well, it's got to be a bunch of matrices that are unitary and have determinant 1 that all commute with each other and as big as possible. And you might guess, and you would be right, that we should use diagonal matrices. They certainly all commute with each other. And it turns out that that is a maximal torus. And I'm writing them as exponentials here because I want to make sure that we get a unitary matrix. Here, e to the I, x, and so on for real numbers here. There's zeros off here. But I want the determinant to be 1. So we want e to the I, x plus y plus z to be 1. That's a maximal torus, you can show. And then you can look at the Lie algebra of that maximal torus. And what that will be, the matrices that when you exponentiate them times any real number, it gets you a guy in the maximal torus. And so what you'll get is just the matrices of the form Ix, Iy, and Iz, where x, y, and z are real. And now the condition that translates into this determinant equals 1 condition is that the sum of the x, y, and z is 0. The trace of this matrix is 0. So you can see that if you exponentiate one of these, you get one of those. Converse is maybe a little harder. And so there's this obvious exponential map. So then, let's think about the kernel of that exponential map. That's supposed to be our lattice. We have the obvious obvious X from V T to T as this kernel. So it's going to be guys like this, that when you exponentiate them, you get the identity matrix. So that means that X, Y, and Z have all got to be 2 pi times an integer. So it's just IX, IY, IZ with zeros off here, such that X, Y, and Z are 2 pi times integers, and they sum to 0. So let's think about what this lattice actually looks like. It's a little, this 2 pi is mildly annoying, and the fact that I'm writing these vectors, these X, Y, Z's as a big fat matrix is also mildly annoying. So let's just sort of change our notation a little bit and just think about vectors such that X, Y, and Z are integers. So I'm dividing by 2 pi here just for convenience, and they sum to 0. So what I've just done here is I've rescaled our lattice, and I'm now thinking of it as a sitting in R3. But what does it look like? That's the thing I'm aiming at here. So, well, you have to start imagining some triples like that. I mean, if you've got really good imagination, you can imagine the integer lattice in R3 and then slice it with a plane X plus Y plus Z equals 0 and just see what you get. But that's a little hard maybe. So, well, it's got the origin in it. It's got various vectors in it. It's got 1, -1, 0 in it, for example. And that will be sort of as close as you can get. One of the vectors that's as close as possible to the origin. But then it's got various other vectors. For example, it's got a vector here, like 1, 0, -1. And if you think about it, that's a 60-degree angle between those two. Well, there'd be another one up here. There's another way that I could do the same kind of thing. I could instead of moving the -1 around, I could move the 1 around. So this would also be at a 60, sorry, that's not right, at a 60-degree angle. So I just pop the 1 over. And then we can just keep playing that game, but we don't even need to keep playing that game because we know that the other 3 are going to be negatives of the ones we have. So we're going to get -1, 1, 0. So we get the hexagon like this. And so these points, you can ponder and think about it, will be the 6 points that are the closest to the origin.
That's +1. Yeah.
Sorry, there. Yeah. Closest to the identity in this lattice. So this is a lattice that I've shown you before. It's called the A2 lattice. Remember the A2 lattice, the way I described it was you have 2 vectors that are at an angle of 60 degrees from each other, or you can say 120 degrees, I was saying 60 degrees. So that's what we get. So in other words, SU3 is associated with this particular Dynkin diagram, to the A2 Dynkin diagram, A3 Dynkin diagram, sorry, A2 Dynkin diagram. And that's how it works in general. There's nothing so special about the number 3 here, except that it's easier to draw things. So what you can see by the same type of thinking is that SUN corresponds to the Dynkin diagram AN+1. Remember, that's the one that has n+1 dots connected by these edges, which indicate that each dot is, well, 60, or if you prefer, 120 degrees to its neighbors and at right angles to all the rest.
Do you mean n-1?
Ah, I wish God hadn't done that. Yeah. It's plus and minus ones are really confusing for me here. Because of like the n simplex shows up and that symmetry group of that is Sn plus one, and there's like always up and down by one, yeah, but I can't, it's just the way it is. So I'll stop there. So next time what I'll do is I'll show you, just tell you how, and I won't really show you how all the other Dynkin diagrams give you the groups, and then I'll focus on some of the more weird and exciting cases like E8, just for kicks, basically. Okay, thanks. Is that a?
It was a question.
I can do that.
We can clap you first.
Okay.
So can you give some intuition as to why a compact Lie group always contains any torus?
So basically what you can do is you can take a generic element in the Lie group, just randomly pick a Lie element and hope you didn't do anything dumb. And then you keep taking powers of that. They will all, including negative powers, they'll all commute with each other. And they will move, and they'll sort of keep running around the Lie group, and they'll get dense within some torus. If you're unlucky, you might loop back to where you started after a finite number of times, but typically it will like keep spiraling around and it'll get dense in some torus. And so the most generic elements will actually get dense in a maximal torus. So that's sort of how you get them. Yeah. Yep.
Taking up on Sue's question, isn't that the definition of the dual lattice? In the sense, if that's exactly the condition I would write down as the quantization condition of the monopole. In a non-abelian theory, which gives me the dual Lie algebra, not the original algebra.
Oh, well, I'd have to talk to you about how monopoles have to do with it.
But
I mean,
simulate the algebra, wouldn't that be flipped?
I can get completely confused about this. So yeah, so the sort of geometrically easy lattice to get out of a Lie group is the one that I've described.
Right.
And then its dual is also the dual of that lattice. You can talk about a dual of a lattice in the Euclidean vector space, which is all the points whose inner product with your vectors in your original lattice are integers. And the dual lattice is also incredibly important. And basically the bunch of points in there parameterize irreducible representations of your Lie group. Right. So, I mean, it's even possible that what I'm calling the root lattice is what some people would call a co-root lattice or something. Is that right? I don't know. Okay. Yeah, I mean, there are some important mathematical points here and some actual mistakes that I made that were caught. But whether this lattice that I was focused on was the one that someone else calls the root lattice or not, it's probably important when I write up things to be nice. But the point is that this lattice is the one that you quickly get from the torus, and it suffices to classify the Lie group. So I mean, that is basically all right. What I really recommend, by the way, is Frank Adams' book, Lectures on Lie groups, I believe it's called, and he gets a hold of this lattice in basically this type of manner, and he does it not just for the compact semi-simple Lie groups, but for all compact groups. So he sort of folds the abelian case in there as well. And I find that much more, my treatment is sort of vaguely based on that. I find that a nice approach. Yep.
So just to be clear, is the hidden magic here that any reflection of this lattice here is given by conjugation from something in the Lie group? And is that the
Yeah, that's right. Oh, I was like rushing so fast, I forgot to say that if you look at what you get when you start conjugating the torus by elements of the Lie group, you just get permutations S3 acting on these diagonal matrices. So I'm saying that if I'm not saying it most articulately, but I'm saying if you take an element here in the if you take an element here in the Lie algebra of the maximal torus and you start conjugating by guys in SU3, all that can happen to them is they can get permuted. And so those permutations are also going to be some active symmetries of this lattice.
And do we also get the other way around that any reflections on this lattice is also
Any reflection along any one of these 6 points will be in the Weyl group.
okay, potentially something.
This is a particular case, by the way, where there are these other points, like right up here, for example. The reflection along them gives you other reflections that preserve the lattice. I mentioned once upon a time that this hexagonal lattice in the plane is the root lattice for 2 different finite reflection groups, one of which is the one we're talking about here, which is A2. And for that one, you just use these 6 vectors as roots, and you just get the symmetry group of the triangle, not the full symmetry group of the hexagon. And then the other one is G2. Well, now I'm drawing it in its full Dynkin diagram splendor, but if I drew it as Coxeter groups, it seems like this one will be 3 and this one will be 6. And G2 has the same lattice, but it has more roots. It would have these roots forming this Star of David kind of thing. And so that you get extra reflections from them, and you'd get the symmetry group of the hexagon then. Yeah, but I'm not doing that now. I'm just about A2.
When you define semi-simple Lie algebras,
Yeah.
you define them as like perfect algebras, basically, right?
I guess I don't know what perfect means.
So every element is a bracket of 2 elements.
Yeah.
But I don't think that's actually equivalent. So semi-simple Lie algebras definitely satisfy that. But so is compact semi-simple equivalent to that? Maybe.
Can you tell me why you don't think they're equivalent?
I found an example on Stack Exchange,
Can you tell me what it is?
which is
Okay.
maybe later. Maybe
Okay,
later.
okay. I thought it was true. Yeah, so I mean, there's another much more long-winded but standard way of defining semi-simplicity of all sorts of algebraic gadgets, which is that there are lots of ways that the representations completely decompose into irreducibles, or that it's acting on its So I picked the wrong one, maybe, although I'll think I'll look that up and talk to you about that. Yeah.
On this story, only works over complex.
Everything here was actually working over the real numbers. So the compact Lie groups have real Lie algebras. They do not have complex Lie algebras, right? If you, like, for example, SU3 is a real vector space as its Lie algebra, but like there's another good friend of it called the complex form, which is SL3C. That would have a complex vector space as a Lie algebra. So I was trying to keep the shorty stort by just purely focusing on the compact guys. So I was just doing certain kinds of real Lie algebras. They'd be called the compact real forms of some complex semi-simple Lie algebras that you might have read about somewhere else.
Just to let you know, the camera's just cut out. No, I mean, not that you're writing anything anyway, but maybe that's a hint.
Okay, maybe we should stop. Yes, thanks.